Okay, so this lecture is not new material, it is review, because it is time to acknowledge that we've covered a lot of ground, learned a lot of reactions, just highlighted in many of these circles here are various functional groups we've encountered during all these transformations we've been learning. And it would be appropriate if right about now they were kind of swimming in your head and you were making sense of how to connect them, hopefully using the roadmaps I've been encouraging you to use, the reaction roadmaps. We're going to elaborate on some of those today, but I'm hoping that it's a very valuable exercise to make those on your own. And what are they useful for? Well, this is one of the ultimate goals of organic chemistry, is to be able to synthesize a molecule. And so if you're presented with this sort of multi-step synthesis, you've got to know how to interconvert all these possible pieces. This is basically the tools in your toolbox. You need to know which ones are appropriate to apply. And starting with an alkyne, which is our friend over here, we know there's so many possibilities that can stem from that. And so we really want to not just know what can come out of an alkyne, but how an alkyne could connect ultimately to an ether or an epoxide or to a carbonyl-containing compound, right? So that's the goal for today. And so get some paper ready to copy down some roadmaps yourself. And I hope that inspires you to build your own from that point forward. Okay, so going back to our collection of functional groups that we have learned how to react and interconvert between, what you've hopefully been doing all along is, as I've urged you to do, is to create roadmaps for each individual part. So there's one that I took a picture of that I've done on the board before. And so I urge you to do that for each and every one of those. So this is an alkene roadmap, but I could draw alkenes so many different ways. So I drew a cyclic alkene in this example. So feel free to use this, of course, for your own and check against your own. But I would urge you to not, put this away, cover it, and then try to reproduce it. So notice that that would just fit over in, where's our alkene? Right there. So that's one of many that could actually fit in there. And so each and every single one of these functional groups, especially the ones that had a whole chapter focus, like alkynes and ethers, epoxides, alcohols, and of course alkenes, should have at least one of these clusters of various ways. So in addition to the cyclic alkene, you should have a monosubstituted acyclic alkene, disubstituted, trisubstituted, and all the variations that can come out of it, and kind of make a big stack of papers for each and individual one, and then try to get the big picture when we're done. So if you're piecing together all these roadmaps and finally able to put it together in a retrosynthesis, that's actually very rewarding. It becomes like a logic puzzle or game if you're doing it correctly, and that's the level you want to achieve. In fact, speaking of games, I'm going to bring back this classic, good old Zelda. Now he's resembling a lot like what most students look like as they go through each chapter. Light is shed on a particular area that he's exploring, but the rest is in the dark. And so what he really needs, he would like to have the lights on so he could see the whole big picture. And other versions of this game kind of manifested that same sort of one discrete understanding at a time, or one level, one room at a time, if you will, if it's in a dungeon. He didn't have the map or the compass, even better. So you need to have not only maps for each reaction chapter, at multiple maps actually, you need to have the entire picture of how they connect in order to do a retro. And so that's kind of the goal, is to kind of reinforce ways that we can approach that level of understanding. So Link's not there yet, but once he gets the light on, or, in some dungeons, the map and the compass, that helps achieve that goal, where you see the big picture. Okay, going back to our collection of functional groups that we've encountered recently. We haven't looked at how many there are, and we have not, so we've learned reactions with all of these at least, and yet we did not have that many chapters to cover. So it was organized into those chapters for a reason. Alcohols, for example, so we'll put the alcohols in one spot, and we're going to try to organize it kind of by, like the dungeon rooms, chapters, and then that should actually hopefully sort of make it a little more clear how they interconnect eventually. So remember that we covered alcohols. Ethers are epoxides are really just cyclic ethers, so they go together really well. And don't forget, of course, we started this whole journey with alkenes, and shortly thereafter alkynes. And so I'm just going to shrink them down to make sure we have enough room for all of this. And then we, those were our chapters. So we're going to pull from this pool as we need to. But for now, I'm going to try to draw the arrows emanating out of these chapters to connect them. And this is not a specific roadmap. So once again, each of these chapters has many roadmaps for the different scenarios. Like for example, alcohol, you should have a roadmap for primary, secondary, tertiary alcohols. For alkenes, you should have a cyclic alkene, a monosubstituted, a trisubstituted, disubstituted, tetrasubstituted, just to have all those variations for practice. For alkynes, terminal and internal. So we're just going to show kind of a rough relationship, not every single detailed reaction, but I think it still is helpful to see the big picture this way. So then you can distill it down into smaller subsections and take a look at each individual component. So if we recall what happened with alkenes, I'll start with that one first. One of the simplest reactions is we could take them down to alkanes. So look, I have an alkane right there. And so I'm going to move these out of the way. And since I am starting to draw some arrows and starting to write, I'm also going to label everything. So we have our alkynes here, because connecting the word is actually pretty important. The way you process it in your mind, where you're talking, you're actually usually using the language, not just the structure or description. So alkenes, alkynes, alkenes, alcohols, ethers, epoxides. And we can take them to alkanes. What do we do for that? Reduction. So just recall that that's a dead end. So once we're there, there's nothing we could do with the alkane, at least not yet. So you're going to not want to go there unless you're done with the synthesis. You don't have to go. So this has no arrows emanating out of it, in other words. Okay, what else can alkenes do? Well, we've learned how to make alcohols from them. So hydration. So that might be H3O plus or HGOAC with sodium borohydride. And so remember, these were the Markovnikov scenarios. But we can also hydrate and get to an alcohol the anti-Markovnikov way. And notice that this isn't specifying one or the other, because this is a generic relationship. But we want to remind ourselves, if we have to ask that question, do we know which one to choose, right? We need a Markovnikov alcohol or anti-Markovnikov, which is the BH3 THF with H2O2 and AOH. The anti-Markovnikov. And remember, there's also syn selectivity of the H and OH. So I'm going to underline those important stereo selective features. Okay, so remember, so we had 3 ways to get to an alcohol, but that wasn't the only kind of alcohol we can make. We could have also made a diol, right? So we learned how to make the vicinal diols, syn diol. So OSO4 and NaHSO3. Let's take our diol. Where did it go? Here it is. I can label that one vicinal diol. So remember that syn relationship when we use OSO4. And we could also do that with KMNO4. That's sometimes used as well. That's another oxidizing agent. Okay, so now we've made an alcohol. We've also made halogens, right? So we can make the vicinal diol. We can make a vicinal halide, dihalide. So remember that had to do with the Br2 or X2, right? CCl4. So it could be chlorine as well. So vicinal, where did you go? Right here. There's a vicinal halide. So I made those green because on our model kit, chlorine at least is green. It's really obvious. And then because bromine's a little more orangey, which looks a lot like the alcohol, which is red in our model kit. So when I had an alcohol added, I color coded it red. But a halogen, I color coded it green, just so we can kind of spot it quickly. All right, but remember that if we did not have our carbon tetrachloride as a solvent, instead we had water or alcohol, we would not get the dihalide. Let me write down the dihalide first. Vicinal dihalide. We would instead get the halohydrin. So it's kind of right in between having alcohol, the diol versus the dihalide. We have one of each. So this is the halohydrin. So if that was a chlorine, it'd be chlorohydrin, bromine, bromohydrin. So remember that came from having our X2 mixed with water, but we could have also mixed it with alcohol and had it ether. So I'm going to put in parentheses R. Let's just underline in blue so we know what that means. If you had ethanol, you'd have OET instead of OH there. And so it's just a protic solvent would do the trick there. And remember, the thing that was interesting about halohydrins is that if you add base to them, you would take off that OH. And as a result, you'd have an O minus. And the O minus can do an internal attack because, hey, O minus is a nucleophile. Well, guess what? There's a leaving group on that same compound. Attack, kick off. So let's draw that connection because that gets us to epoxides. So I was going to tell a joke about sodium, but I decided, nah. Okay, just making sure you're awake. The NaH would do a good job taking off our H there. That way we have an O minus, attack, kickoff. So now, actually we don't need anything else. I was thinking of it as 2 steps because it would be 2 steps from the alkene. It's only 1 step here. So there needs to be no number 1 there. There we go. All right, so that's just an SN2, internal SN2. So, when you write these little road maps, write whatever notes to yourself you need. I think it also helps a lot for me to put the key step of the mechanism somewhere in there, just, mention it. Because, for example, it's not always shown in such a generic case like this, because this is monosubstituted alkene, but this is a trans relationship that's here if this was not monosubstituted. Since there's no stereo center introduced, then we don't even see that result. But I might write those little notes because remember there's that bromonium ion intermediate that gets attacked at the opposite end. So I might just write trans X. They have an anti-relationship. So anti is the other word you want to look out for. So same here. These are anti. OH and X. That's what the mechanism dictates. So I like to underline some of these little notes in a different color. Not just anti, that's their stereochemical relationship, but the regiochemistry is pretty clear there. Notice that the OH is on the more substituted carbon. And that comes from the mechanism. And does the mechanism belong right here? Probably not. It's probably better in the alkene only roadmap, because otherwise that defeats the purpose of keeping this as general as possible and just making the big picture connection. When you want to start diving into the details, then you open up the page on the alkenes where it fills the whole page with all the details. Okay, but that's about as far as I would go in this. This would be like your big poster if you had a poster board. Okay, so we can arrive at epoxides. And so from a halohydrin, and we can arrive at a vicinal diol. Diols are something we've seen before also from epoxides. We can open epoxides to become a diol. So remember, that can be done with acid or base. So basic attack or acidic ring opening. They both give us the 1,2 diol. The only difference is this gives us the anti-diol option, whereas this osmium tetroxide gives us the syn-diol option. And notice, because we kept the generic, we would have to, we don't see that stereochemical relationship here. We have to have that in more detail on another page, but that's why I'm writing it here, just as a little reminder. So we've made from alkenes, we've made the dihalide. Let's go for the monohalide scenario. I'll draw it next to the alkane because we're adding an H instead of H2, we're adding HX. So it's similar in that way. So let's have an R group here, and then we're going to have the possibility of having the Markovnikov or the anti-Markovnikov. So let's give ourselves some space over here. So how do we get the anti-Markovnikov? HBr and ROOR. So just that addition of the peroxide changes the selectivity, the regioselectivity. So here's our Markovnikov regioselectivity, and here's our anti-Markovnikov. And so this is the, notice I didn't make a separate, sort of circle for this, but these are alkyl halides, right? This is back in SN2, E2, those were the main focus back then. But so that opens up the door to SN2s and E2, etc. So I'm just going to leave those there because we can imagine all the possibilities we can arrive at from that. So I'm going to say to SN2, E2 maps. We have not drawn an arrow to alkynes yet. We know we can go this way, the other way quite easily, right? H2 Linlar. We'll stop at the alkene. And remember, if it's not a terminal alkyne, which that alkene appears to be terminal, so that's the limitation of these kinds of roadmaps. You have to specify something, and then by the nature of doing that, we'll exclude some reactions. But it's just worth noting here. Since this is terminal, the one I chose to use as an example, we would not use the dissolving ammonia, sodium and ammonia, liquid ammonia, and that's because it just deprotonates the terminal alkyne. It doesn't do the reduction. So the NaNH3, in other words, we need that for this one. So that would be on the roadmap specific to this. But the general idea is we can reduce to an alkene, and so that's with H2 Linlar. It stops at the alkene because remember, without the Linlar, without the poison catalyst, we go straight to alkane. So that's the levels of reduction. 1 equivalent H2, 2 equivalents of H2. Now to go backward, we have to gain a pi bond. We know that to gain a pi bond, we need to do elimination. And we know that to do elimination, we need a leaving group. So we need a halide, right? Which one do we need? If we add only one, like HX, then we only have one pi bond that we can add, which will just take us back. So we need to have two leaving groups. So this guy would do the job. So we're going to do a two-step sequence to get to an alkyne. We can't do it in just one step because we need to first install the leaving group. So Br2, CCl4, and then 2 double dose of the base. So we'll do excess and then pick a base. Like let's do sodium amide. And so of course I'll say excess here too, because we'll do more than one equivalent. All right, so that gets us to an alkyne, and that unlocks a whole host of other reactions as well. So why don't we do some of the familiar ones like HBr, HX. We'll add that to our alkyne, or HX. And we'll do excess because we have 2 pi bonds this time. And so remember what happens when you think through the mechanism. 1 pi bond comes and grabs an H. Then we have a plus on the more substituted carbon. That would be this one if it's terminal. And then that would allow the halogen to go here. So it's Markovnikov selection again. Repeat. Halogen goes here a second time. So in other words, two halogens share a carbon. When two halogens share a carbon, we have a vicinal dihalide, and that's actually one of our options right there. Excuse me, I said vicinal, it's geminal. So I'm gonna write that out. They're twins, share the same parent carbon, geminal dihalide. There's a nice spot next to the vicinal dihalide, just to distinguish that. But so that's one type of halogenation. Remember, we also added H's that weren't drawn. So if I had called this DBr or DX, D's would go here, two D's, two deuteriums. So that was the addition of two equivalents of DX or HX, if that's what we were to do. But if we wanted to, instead of doing the HBr or HX, the BR2 or X2, we could do that as well, and we'll have all our halogen possibilities up here. And we need excess to react both pi bonds, and we'd get anti-X's there, and then a second time, and then it wouldn't matter. There's no stereocenter to worry about anymore. So we end up with this guy that's got 4 total halogens now. So I'm going to call that a tetrahalide. Tetra, so 4. These are kind of important keywords to kind of set them apart. Okay, so we also learned we could hydrate our alkynes with the similar hydration conditions. So if we added, for example, instead of H3O plus, like we have here, HGOAC2, with kind of like a combo deal there, we have often HgSO4 and H2O. And so what that would do is add one equivalent of water across that pi bond. And so the OH goes Markovnikov, the AH goes here, so that pi bond's gone. We have an enol that tautomerizes to the keto form. So that's generically represented here. So you have to watch out for that, because there's another way to get it, which is the dicyamylborane, which is really only useful for a terminal alkyne, so we can get the selective anti-Markovnikov. So we'll write that out here. So this would be the Markovnikov. That gives us the Markovnikov enol, which tautomerizes to the keto form. And then if we have the dicyamylborane for a terminal alkyne, so that's that bulky borane. So that's just one of the most popular ones, but there are the other ones like 9-BBN, for example, and H2O2 with NaOH. Then this is where we get the anti-Markovnikov enol, which gives us an aldehyde when we're done. So this gives us a ketone, this one gives us an aldehyde. Just as an extra little reminder, I'm going to put an exclamation point under the aldehyde ketone, just because we are simplifying it by having this all land in one circle. Okay, so now remembering all these connections, we're still not done, but a lot of this relies on, once again, foundational practice of the mechanism. So working through this, in fact, a very reasonable mistake would be to think that these would hydrate twice, giving us a geminal diol. But we don't actually see geminal diols in this class. I put this in here as a reminder that you got to keep working through the mechanism and make those connections, that this is not formed. So we're going to do away with that one. And we will see it in 212. Don't worry, it's coming back. And so, yeah, the only geminal functional group we have to consider is the halide. So it doesn't happen with the alcohol because of the tautomerization. So the keto-enol tautomerization. So just keep that in mind. I might even put that, I don't want to put that here because there's other ways to form a carbonyl. So I might even put that in green. Tautomerize. Okay. There's other ways to form carbonyls, like I said. There's one we didn't write from our previous alkenes. How dare I, because that's also one that's considered pretty fun by most student standards, is the ozonolysis. So those are, we're going to cleave the alkene, oxidative cleavage, and arrive at a carbonyl compound, either a ketone or aldehyde, depending on what's attached to that alkene. Now, you may also remember other ways to arrive at a carbonyl, and that would be from the alcohol. So let's connect those in. We're going to have to go down under here. And so remember, that would be the PCC, and that would have to stop at the aldehyde. So I'm going to write that. I'll write that in a different color because that's a side note. Or you would do the Jones reagent, which is depicted in lots of different ways, Na2Cr2O7 or H2CrO4 as chromic acid, or CrO3, H2SO4, H2O. So there's different ways to write these chromates out, but they're all collectively sometimes just written as Jones. And so that's the strong oxidizing conditions that do not stop at the aldehyde. It goes all the way to carboxylic acid. Or ketone. They both would go to a ketone for secondary. Oxidize primary ROH to carboxylic acid. So the primary ROH here would stop at aldehyde. Remember that if it's secondary, it's a moot point because it'd be a ketone no matter what. So I should actually add, not only could we have a H, so notice this notation here. It's a ketone if there's an R. If we have an H attached here instead, that's an aldehyde. So that's a way to really generalize this and make these connections a little bit more simple. But there's also one that we could have added, which is a carboxylic acid. So we arrive at a carboxylic acid from Jones from a primary alcohol. We arrive at a carboxylic acid again by ozonolysis of an alkyne. And remember, it's a water workup for that one. There's a lot of other workups that we could use. You're only learning those two, so don't let that throw you off too much. Let us not forget one of the most important reactions and simplest that alkynes can do is deprotonation, acid-base. That's step one. Then we get our nucleophile that can do all kinds of things. So if I write the alkyne, of course this would only work with a terminal alkyne. So that's supposed to be a lone pair there, but it's hard to see. So we have our nucleophile that can go and attack, and this is our CC bond forming reaction. All right, so that could go attack other things, other electrophiles. What electrophiles is it attacked? It's attacked epoxides and opened them. It's also attacked any of these alkyl halides that can undergo an SN2. So you want to watch out for that one. That's very key in synthesis, right? So I might even just remind ourselves, let's put that little circle right there just to keep an eye on that one. CC bond forming reaction, big deal. Okay, let's round out that other side. Alcohols become ethers. How do they do that? First, you need to add something to take off that H, so some sort of base, like NaH. Then your alkyl halide, so R prime X of some sort. So of course, you've made that alkyl halide many times before. This is just an SN2. But this SN2 has a name reaction. This is called the Williamson ether synthesis when you do that sequence of base followed by alkyl halide. Ether synthesis. Of course, other leaving groups would work as well. You just have to follow the SN2 rules. But what happens is we needed that alkyl halide to do the trick. So we could have just as well drawn an arrow from here or here from one of the alkyl halides to work its way over here. So I'm going to go ahead and draw one. Just to remind ourselves that we have different points in here where of origin, right? So I'm going to do that here too. So we have, instead of we starting with alkyl halide, we need the alkoxide. So I'm just going to call this, oops, I erased part of it. I'm going to call this RO prime, or R prime O minus. And this is Williamson ether once again. Just another way to draw it. And while we're keeping all the connections going, this is really old stuff, but we should remind ourselves that these alkyl halides can become alkenes. So E2, strong base. So let's just use one of our favorites. All right, so that's because we have this, I didn't label, I did label alkyl halides here. So now if we branch out from these epoxides, now notice this epoxide has a substituent on it, but there's no stereochemistry indicated. So once again, it's worthy of its own separate roadmap, but just to try to tie everything together, we're going to visualize, make this as generic as possible. So the two things you really have to usually be concerned with, other than the first time we saw epoxides open, which is when water was added to it. So in other words, we got a diol. But by this very same mechanism, we can have other nucleophiles attack. So instead of having an OH minus or water attack to open the ring, we could have if in the case of acid, we could have HBr. And then the Br is the new group. In the case of base, we could have acetylene attack and open it up. We have a new carbon-carbon. We could have Grignard attack and open it up, right? So things to keep in mind, just to keep that as generic as possible, and then you want to refer to its own roadmap, is let's call that one of two scenarios. Nucleophile with a base condition, so basic, okay, or the nucleophile, which I'm not even going to call it negatively charged because it's under acidic conditions. So it gives us different outcomes. So our R group's still there. It's just a matter of who gets attacked. So when we do a base, remember that's an SN2 style attack. It goes to the least substituted position. So the new group ends up on the least substituted carbon. That means the alcohol is formed thanks to the epoxide oxygen no longer being part of a ring. So this O came from the epoxide oxygen. The new group, of course, is a nucleophile. So note, that's really no different than the diol. One of these came from this oxygen, one of these was the new group. It's just that you're forced to distinguish the regiochemistry once they don't match. So now we're going to do the same thing under, how does that compare under acidic conditions? Remember, that's an SN1, SN2 hybrid. Let's circle these mechanisms just to remind ourselves. So as you talk yourself through that, you say, okay, SN1, SN2, what does that mean? It means I protonate with this H, starts to strain the ring, with the bond starts to break in one of the two carbons. Where would it break first? Well, wherever the better carbocation is, the better carbocation would be where it's more substituted. Therefore, the OH detaches from there, the O that has been protonated with an H detaches from there and stays on that end carbon. So our framework will start off looking like this as we talk through that OH. That means our new group had a partial carbocation, so the nucleophile attacked preferentially at that position. Note that regiochemistry is distinctly opposite of the scenario right above, so we have very different outcome. So that's why I say this is worth having its own sheet with the little mechanism fleshed out, but in terms of summarizing, here we go. So we have our, it's hard to really name this functional group because it depends on what it was. This nuke, it could have been various things, various nucleophiles. Alkyne, Grignard, nitrile, so anything that you can think of that can act as a nucleophile that you learned from SN2 chapters would apply here. HX, right? That's another one. We could have had, we can make ethers with ethanol. I could just go on and on. So that's good to keep that in mind, that these could actually reconnect to other areas. It's more complicated than it looks because it looks like there's very few arrows coming out of the epoxide region. Let's do another name reaction, the Grignard reaction, named after good old Victor Grignard. Here we go. So the classic one that we covered most of the time was the Grignard, which is, R, Mg, Br, How did we make that? That was from alkyl halide. So look at all these arrows. Look at all these connections coming in. So we needed magnesium, elemental magnesium. And so that would make our Grignard reagent. And so that's our carbon nucleophile. And so then step 2 would be water, just to neutralize. It's a workup. And I'm going to highlight this one once again because it's one of our carbon-carbon bond forming reactions. It's the only other one we've done. So just to highlight one of the most important parts of it, I'm going to put a little prime there and note that it adds new R group. Okay. So this is by no means exhaustive. There's other connections. See if there's any more that you want to fill in or ways to flesh it out, like defining the nucleophiles up here. There's one more I'm thinking of I want to put in here, which is we've had a reaction that only syndials can do. So remember when we had osmium tetroxide? And it might get a little messy to do this, but we can do it. Get an arrow all the way to this ketone section again. Let's go over the top instead of the bottom. So we can go this way. So remember that we can cleave syndials with HiO4. Let's see, I'll put that over here. Make it close to it. So that was an oxidative cleavage, but that only works on syndials. Just keep that in mind as yet another way to arrive at ketones and aldehydes. So they pop up, but notice a couple things when we step back. Only one arrow comes from a ketone aldehyde, so think about this synthetically. If we have a ketone or aldehyde, we have lots of ways to make it, so all kinds of oxidations. However, we only have one way to react it so far. 212 is where we unlock the ketone aldehyde chapters where we have lots of ways. So it's not that they're difficult to react, it's just that that's reserved for later. So Grignard is the only thing that converts it. So if you know that was an intermediate, you know, and a new carbon-carbon bond was formed, you know you used a Grignard. And we'll always want to kind of take a look at the roadmap, make sure we're not missing out on anything. So it looks like our ethers has a lot missing. So let's notice that I didn't draw an arrow coming out. And we know that we can actually hydrolyze those, right? So those can be turned into, if you had acid, they could be turned back into component alcohols. But the one that we really focused on was turn them into alkyl halides. So excess HX will get us to the components of the ether. So the Rx plus, I'll just even write that here, goes to Rx plus R prime X. So you get the two alkyl halides. Another thing to point out is that this is a master map, if you will, to help you kind of with retrosynthetic planning for the most part. For, you know, multi-step transforms is where this sort of studying is very useful, but it's not exhaustive in terms of conceptual, mechanistic probing. So this is the synthetic sort of kind of tool that you need to have to make those connections. Now, for example, what I mean by that is epoxides do other things that we're not going to see as much in a retrosynthesis problem. Like they, remember we saw them polymerize, and you can add that to this if you want, but that's not going to make a connection anywhere. It's kind of a dead end. We can polymerize, and that's a useful thing to remember, but it's not usually part of a long retro. Another one that you won't see as much part of a retro that still is a useful reaction is the pinnacle rearrangement. So how do we get to those? You need that 1,2 diol. And that would eventually, kind of in a similar fashion, except there's no oxidative cleavage, go down to a ketone. But it's not this, it's got a rearrangement involved, and usually in a retro, for this class, we're going to avoid lots of rearrangements along the way. So this I'm going to refer to as kind of your master roadmap for synthesis. You know, it's the best way to study for synthesis. So master map. Let's call it our master map. So when we refer to it, as opposed to our little mini roadmaps for each that are functional group specific. So I think we did a good job of connecting all of them. So you would say that maybe, let's box this up. Suspenseful music. Yes, so that means that hopefully we have the tools to do a retro. So let's give that a try. All right, so I got my master map handy, and I'm going to do number 1. This is a workshop problem for retrosynthesis. And so hopefully we see the value of kind of organizing. Took a while. That was probably half an hour in the previous slide, but it's worth organizing all your thoughts. It pays dividends in the future to have that ready. So a couple things to note. We're starting with an alkene, and we're ending with a diketone. 2 ketones, so we call it a diketone. So I always write out the name of the functional group just because sometimes that makes a mental connection that you might not otherwise have made before. And so notice that it's also a ring, cyclic, and now it's acyclic. So I'm just making some observations. The other thing that's always necessary is to count your carbons. So I'll start here, 1, 2, 3, 4, 5, 6. Okay, so let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the 6-membered alkene became a 10-membered acyclic diketone. Now notice that we're also allowed to use only the carbon sources provided, so acetylene is also provided there. So we clearly are going to use the carbon-carbon bond forming reaction of either acetylene or converting that to a Grignard reagent. So let's get started in planning this. So we know that we increase the number of carbons. So that means we have to use Grignard or, so those are the 2 I highlighted, or acetylene, SN2. So in other words, remember this map, we highlighted the Grignard, oh, it got cut off a little bit, is over here, and then the acetylene one. So keep in mind that that narrows that down greatly. If we know we have to incorporate that in order to use acetylene, we have to have a leaving group. In order to use Grignard, we have to have a carbonyl that we attack. So that's both of those things are possible. Notice that it went from cyclic to acyclic. So that means we must have done, the only way we know how to break a carbon-carbon bond, so that's also equally important. So very few ways to make carbon-carbon bonds. And we also broke carbon-to-carbon bond because it's no longer in a ring. So that means we had to do either some sort of oxidative cleavage because carbons are not leaving groups. So that means we had to use O3 or HiO4. And it turns out there's lots of different routes that work. So let's pick one. So let's do the ozonolysis. So that's as kind of our starting point because that really narrows it down greatly. So that means that these used to be connected. Okay, so now we could either go backward or forward, or a little bit of both. And this is an example of a problem where I actually kind of like going forward first because I've seen that breakthrough with the ozonolysis. But another student studying this might actually see something different that's worth working on. All right, so I feel like the ozonolysis looks like the most straightforward necessary path in here, or is the oxidative cleavage at least. So I'm going to work forward up here, and I'm going to do that ozonolysis step. 1O3 to DMS, dimethyl sulfide. I'm going to number my carbons. That's always important because if I don't, I could easily drop one. And remember, a good way to avoid dropping one in ozonolysis, especially if you're doing a ring, is to draw all the carbons that were in the ring and then just cut that pi bond in half and then put the 2 oxygens on either side. So nevertheless, renumber to be meticulous and certain that, there we go, 6 carbons, good. So now I'm on my way. This equals, we'll let that rotate. We have, so 2, 4, 6. We have an aldehyde, a dialdehyde. We need a diketone. That's where our carbon-carbon bond forming needs to come in. We need to make bonds here. And the only, so remember our roadmap. Here it is. We can have the, we're at this step where we have a carbonyl and we want to know how would we make a carbon-carbon bond with it? Well, the only arrow emanating from the carbonyl in our roadmap is the Grignard. And so that's our only choice. We don't have any other arrows coming out of the carbonyl. So if you know you've made a bond to a carbonyl carbon, and furthermore, it's a carbon-carbon bond formation, has to be Grignard. So let's minimize this guy back down and prepare to do a Grignard. To do a Grignard, we need RMGBr or RMGX. So we need something like that, RMGBr. So now it's time to do a little bit of backwards work. What did that RMGBr look like? So we did our O's analysis. This is from O3, that green part. But if we go back a step and say, okay, this may be even maybe a few steps. We're not really sure. We know that we got to the middle, sort of, right? We got to one of the intermediates with this. But what would have attacked it? So these pieces here are the new carbons that are unaccounted for. So we say, okay, it's carbonyl, and we added ethyls. And the only way to add ethyl is in the form of a Grignard. So ethyl magnesium bromide. Okay, but this is not an allowed starting material. These are the allowed starting materials. And we've already shown that this can go back to this guy, but we have to show how we make the ethyl magnesium bromide. That's where it comes from here. So that's two carbons, so we're set. 1, 2, or 7, 8, if you will. All right, so how did those get made? The only way to add the magnesium is to an alkyl halide. So that came from the corresponding ethyl bromide. In other words, if you add magnesium to that, you get ethyl magnesium bromide. A monohalogenated alkane. Well, look at our roadmap. How do we get there from an alkyne? So our roadmap would tell us, okay, monohalogenated alkyl halide. We can ultimately get there from an alkyne, but there's no direct path. So notice that there's not an arrow this way to the alkyl halides. So we go alkene, then HX. That's monohalogenated alkene, right? Or alkane, excuse me. Let's go back, shrink this guy. So that means this used to be the alkene, which used to be, so in other words, HBr would fix that, which used to be the alkyne, which means that H2, but stopping part way, Lindlar, partial hydrogenation. All right, so if we write out the complete forward synthesis, we would have step 1, OA, because it's a part of the same step, O's analysis, O3, and then B, DMS. Step 2, we had to throw in our ethyl magnesium bromide, but that's an AB thing too, with water. How did we make the ethyl magnesium bromide? So we had acetylene, step 1, H2 Lindlar, or step 1, excuse me, step 2 would be HBr. Okay, so it's really not a whole lot of steps, but the roadmap hopefully proved its purpose as something to kind of help solidify those connections. Now, I urge you to go forth and try your best at the other problems on the sheet, the keys posted, but it's very good practice to work your way around various transformations that occur on that roadmap.